Okay. Let's start this other session. We have two presentations about template metaprogramming and generic programming. The plan is to do this thing in an hour. Then we have a static initialization presentation. Let's see what happens. So I received a couple of questions, like I want to see how these things that are showing us to be actually used in real code. And there will be examples tomorrow when we do the proxies, and also today with the generic programming. That are kind of real-world examples of when these things are actually used to produce better code. The problem is that, as I was mentioning yesterday morning, you cannot decouple performance issues from API issues. So if you want to use C++, it's not because you want to be fast, because you can be fast with C, you can be fast with Fortran, or you can be fast with assembler. So write your application in assembler, you'll be fast if you know how to program it. So you don't write C++ because it's faster than other languages. It's faster than other languages and gives you, provided that you would give the same interface, the same API. So you can develop APIs, even embedded domain-specific languages, as they're called, in C++. You cannot do it in other languages, and they are efficient, but you cannot decouple the API design from the efficiency. If I tell you how to be efficient in C++, it will be exactly as I tell you to be efficient in C or in Fortran. If I tell you to be efficient in C++ and get the good APIs, I need to explain all these things because this allows you to implement the functionalities that makes this thing possible. So hopefully we will get that. We'll get there. We'll get to real examples that shows that you can have good APIs and good implementations. But the APIs are not something, okay, if I have time, I do also a good API. No, you have to design the API with your application all the time. Otherwise, your project will suffer in the long term. And now let's go to template metaprogramming first. So another step forward, a little more high level. So classes have several different kind of data members, different kind of members. There are data members, can be static. You have member functions, it can be static also. It can be context per functions and members, as Paulo will show you tomorrow. Static const data members, they're actually available at compile time. I have also type members. Strangely enough, the type members are never really mentioned anywhere. They're there, but they're called type members in kind of informal way. But basically, you can have a type def inside your class, and it can be public, it can be private, and you can access that type information from outside if it is public. So what we are interested when we do template metaprogramming is context per function, nested type names, and static const or context per data member. Metaprogramming means manipulating types and manipulating const values or compile time values. The main mechanism is to use class templates. So templates that we've seen yesterday afternoon and all the details and how the specialization works, how the selection, etc., will be exploited in great detail in template metaprogramming. Usually, if you write your own application, you don't need much of template metaprogramming. It's when you write abstract code that you need it. When you write what you call a generic library, for instance, that we'll see later. But when you are designing interfaces at a high level, and the user can use those interfaces, and it can handle all different kind of possibilities that the user might come up in his mind. And in that case, then these template metaprogramming basically arises from there. You have to use these techniques in order to make your program, make your library work for the cases that the user wants to. And it's extremely useful, actually necessary in header-only libraries, the one I was mentioning before. You don't link those libraries. They're not binary files somewhere. They're really included into your translation unit, and everything is compiled, and the template will be instantiated and then compiled. Then you create an object file for this. So it is a tool for creating libraries more than a tool for creating applications. Either header-only libraries or even object libraries, because the object libraries do not have templates, but you can use this technique to generate the proper library. But let's look at one example. We want to compute the factorial of 5 at compile time. So we say we have a struct factorial, which has a static const expert data member, can be static const data member, which is an unsigned value, which is equal to n times the factorial of n minus 1 colon value. And n is, this is a cut and paste issue. In my code, I think I'm using const char because it doesn't make much sense to compute factorial for a number bigger than 255, right? So char is enough to keep, but the result is actually unsigned integer because it goes above there. So the input is unsigned char, the output is an integer, unsigned integer. And basically, I take this value, this number, I use it here, and I use n minus 1, factorial n minus 1, colon value, and I instantiate another factorial with this number. Then I instantiate another factorial with n minus 2, n minus 3, and until I get to the specialization here. Remember the specialization I search every time you instantiate the template. So when I do 5, for instance, I have 5 times factorial of 4. It goes to the primary template, look for this guy, then search for a specialization. It doesn't find specialization, it goes with the primary template, and goes on until the factorial gets a value of 1, with n is equal 1. In this case, the factorial of 1 is 1. And so then you can write factorial of 5 colon value, and you get this thing. And this is a very complicated code to basically move 120 into a register. We can actually see it. In our compiler explorer. Ooh. Oh, the cut and paste didn't work this time. Why? Oh, too bad. Oh, crap. Okay, let's see this. Oh, why? Oh, okay, let's go. You have some example, okay. Main function. And look at this, move 120 into the ESI register, which is the one that is passed, the argument passed to the STD, to the operator less of the standard library for output. So this code is simply translated into a single assembler instruction. This is without optimizations.
That one was with optimization.
That was with? Oh. Oh, yes. Yeah, I guess it's doing all the implementation. Yeah, all the instantiations in this case, but I'm not sure. No, yeah, still get it. A template doesn't have to be instantiated in this case, right? I mean, it's not the function that has to be, it's not the prototype function that has to be somewhere to be called. This is just a static value, is a const. Actually, this is const expert. This is the trick. If it was static const, maybe you could find all these integer values into the data section of your assembly, of your object file. But this is const expert in this case. Yeah, I didn't pay attention to this. But being const expert means the compiler gets the value at compile time, no matter what the optimization level is. So you might wonder why you want to do something like this, and there's all the other examples. Well, if you have to compute the factorial at compile time, but probably not very often. So why template metaprogramming? Well, the same thing as asking why I need a hammer. Well, it depends. If you have to hang a painting, you need a hammer. If you have to watch TV, probably it's not a good idea. So it depends on what you have to do. When you have a generic abstract code, that is where this thing comes out. You have to use it. At some point, it becomes natural. You have to do some of these tricks with templates and specializations to be able to get the results that you want. It can be tricky. It can be challenging. Like this factorial example, it's like just to show you how the thing works. No one will ever write something like this in their code. But very similar things happens. We have in our library a function that computes at compile time the exponential of a number. And this is because we need to know how many neighbors there are on a given array. So we want to see how many neighbors is a number of dimension, something to the d. I don't remember why. We have to do this exponential of this integer value, and we do it at a compile time. We don't want to get function calls or something. Now, there are better ways of doing it. Instead of doing this classical template metaprogramming in some sense, this is the classical way, using the column value to get the static member. You can use const expert functions to do so. So you can have like something that looks like a function that gives you a value at compile time. And this is what Paolo will show you tomorrow. But in the classical way, you just do like this. And it's quite convoluted. It requires some code to write. And it can be tricky. And it can show how smart you are. Really, it can show how smart you are. If you go online and search for compile time language interpreters, you write your code as a template, and then we'll generate the code for that code that you wrote. Specifically, there is a language which is called the brainfuck language. It is actually a programming language. It is named like this. I'm not being rude, is the name. Which is a language that uses only less than and slash and some other of these characters. You can write any kind of program with that. You can write it as a template, and you get the code out. There is actually a compile time game in which you compile every step of the game. So you have the configuration of the game, you compile it, and you get another code with the next configuration. You compile it, you do an action, you compile it, you get another action of the game. Those things are completely useless, done by people with too much time to spare. We have to resist the showing off. We have to resist showing how smart we are. We have to do the things that we need to do. But sometimes it's really so cool that it's hard to contain itself. Template metaprogramming is an accident in C++. The template mechanism was there since the early age. People were using not really very often because it was not efficient. When the compiler got efficient in dealing with template, then someone realized that, well, if I'm just using the template mechanism, I can write whatever computable function I want, in principle. This is because the template mechanism is Turing complete. Is anyone not familiar with Turing completeness? Right? Turing complete means you can write every computable function using just templates. And that was like a discovery, really. It was not designed into that. And you could see it because sometimes this code can be really, really complicated to read. It's like upside down or something. If I have to implement two for loops, two nested loops using template metaprogramming, I can do it, of course. It's Turing complete. I know I can do it, but doing it is a totally different story. It's quite complicated. And template metaprogramming, as I was mentioning shortly yesterday, is really resemblant of functional programming. So if you program in Lisp, if you program in Haskell, or Prolog, I heard yesterday, right? You have an old guy here. And if you program with these languages, you know that the functional programming is the most fundamental kind of programming, which you don't have variables. You generate values on the fly. You compute a function, you get something back, you pass it to the next function, etc. The same thing happens here. It must happen in template metaprogramming because types in C++ are non-modifiable. When a symbol has a type, it cannot be changed until that symbol goes out of scope and you create the symbol with the same name with a different type. So instead, you create a class passing a template argument. You have a typedef in there, and you get that type out. You create a new type, and you get the new type. You never change your types. So the problem is that there's no such a thing as template metaprogramming, really. It has to be defined by the people who use it. And we have to define a convention for how to pass arguments in and to get the results out. And this convention, it has been used in the Boost libraries for quite some time. The Boost MPL library, the metaprogramming library, is a good example. Has this convention that if a struct, okay, I don't show in here. Now this convention is being used also by the standard library, even though in a simplified form. And it is a convention for getting the value out and passing data in. Now, debugging these things is very complicated. If you have an error in a metaprogram, it becomes a template instantiation issue. And you get a compile time error that might be very difficult to read. There is this myth that C++ errors can be very long, and actually it can be. It can have an error. I think the largest error message that I measured was like 50 megabytes of text file. But that doesn't mean it's difficult. It means there's a lot of information you don't need there, but you need to be able to search for it. And we will go into this later on. So error messages in C++ can be understood and can be useful. So the conventions I was mentioning is that if a meta function is a class or a struct which defines publicly a type, a nested type name type, or a nested value compile time available const, static const called value. So for instance, I have a meta function here that have a using type equal something and some template arguments. When I do meta function column type, then I get the type that is the result of that function. If I do value column value, I get the value out instead of a type. In case the type members are not called type, or there are more than one with different names, we don't usually call it a meta function. We call it traits. Now, the difference between a trait and a meta function is really on convention. Right? This is a trait, this is a meta function. The boundary between the two is very blurred. You can have easily a meta function that has both type and value, or meta functions that return multiple values if you want to. One example is what we saw yesterday, is a static almost we see yesterday, is an integral constant. When I say I want my integral constant, oh, good, too smart. Integral constant of type integer, and with the value 7, then I have my integral constant, which takes the t, the type that I want my integral constant to be, and the value. And this declared the value type of this guy as t, and then the value is as an element of value type equal to v. And this is all compile time available. This is just numbers that are passed in. So integral constant int7 column value is equal to 7. So this code will compile. The error is not issued because 7 is actually the number that you want to use. And you can define operations as in the factorial. If I want to add two the integral constant, I can have another class which implements the sum of the two. But let's see one real example. To see a real example, we need to build it up, because we need all the components to then put the components together. So first of all, there is a meta function in the standard library, which is called a rank. Now I'll show you how it is implemented. Rank gives you the rank of a multidimensional array. So in this case, I have an array of type T, which has sizes 3 and 4, and the rank of this array is 2. And I want to know the rank of this array at compile time. So how do I do it? I have a class rank, which is here, which gives me the integral constant, the same thing that we saw earlier, of the type is size t. So suppose this is the specialization, okay? The specialization of this guy is saying that if I'm receiving, I have a primary template somewhere of type of, it's called rank, and I accept an array of size n of type t. I accept this as specialization. When I receive this one, I go to the integral constant size t rank of t column value plus 1. So the idea here is that if I receive an array, a two-dimensional array, I receive an int 3 of 4 is an array of 4 elements of an array of 3 elements. So this will become t4, where t is in int of 3. This goes to rank t value, rank of whatever is left, plus the rank of my entry. So it's 1 plus the rank of what is left. Now, instead of computing the plus 1, I inherit directly from integral constant. an integral constant as a public value data member. So I inherit the public data member, and I can do rank of t colon value, and I get the value of the integral constant. So I'm just using inheritance here. So the primary template is this one. If t is not an array, then the rank of this guy is 0. A scalar has dimension 0. So an array, a one-dimensional array is rank 1, a two-dimensional array is rank 2, and a scalar is simply rank 0. So at some point I will add the rank t colon value will be 0, and I finish my iteration. Is it clear how rank works? So now we have the rank. Now we want to be more flexible. Let's say that the first dimension in a multidimensional array can be left empty because it can be allocated at compile time, right? So the first one doesn't have to have a size. So we can put another specialization here that takes empty, it takes no size, and still it has to be counted as rank because it is an array. It's just not being allocated maybe, it's just the type. It's actually kind of incomplete type. So that guy has a rank, which is rank of t, wherever t is, plus 1. I've repeated the slides, I guess. Okay. Now I want to use this meta function. Okay, I want to show you that this can be useful for doing something. And as I said before, you cannot decouple this from the API issue. What is the interface you want to give to your user, or to yourself if you are your user? In this case, I want to be able to say I want to take an array. In this case, the size is 3 and 5. It's allocated on the stack. And I want to loop over this array applying this function. This is a lambda function. We'll see tomorrow more in detail what that means. And this do something on the elements of that array. And I want to loop over this guy. So looping is a function here. It's just a standalone function. It's a template function that takes 2 template arguments. Then cut and paste. In order to keep the code short, I removed all possible things from the slide, but that gives me errors everywhere. So I take 2 arguments. One is the array that I want to iterate on, and the other one is the function I want to apply. And then I have an intermediate step. So first of all, I need to iterate over arrays of different dimensions. So what I do is I have a primary template for performing my loop, which takes the number of dimensions that I want to loop over. And I create a specialization, a full specialization in this case, for the 2-dimensional array. So in the case the dimension is 2, if the rank is 2, then I go into this guy. And this guy, as you can see, is simply as a template member function. I think this is going to drive me crazy. Okay. So it has as a template member function. By the way, template member functions has the same ability of any other function. It will be instantiated only when it's needed. Otherwise, it would not appear. So it's just a function with an extra argument. Remember, as the t's pointer. So this function will take my array and will take my function that I want to apply. I pass it through R-value references because I won't be able to move these things around. Doesn't matter much. And then I have two loops for I and for j. I loop over 2 dimensions, so I have 2 nested loops. And I'm using another STL provided function, which is extend, which gives me the numbers. So x3, x35, this guy here. Then I will have extend 0 will be 3, extend 1 will be 5. These are numbers available at compile time. And I'm using just STL. I'm using my rank function just because I want to use that, but I can use the STL version of the rank. So now I can do loop. When I'm in this front-end function, say this intermediate layer, I do the looping, and I instantiate my do loop with the value of the rank. So I compute the rank, say I have a 2-dimensional thing. Then I instantiate my template. It goes to the specialization with 2 loop nests. And then I say go, and I pass my data, and I pass my function. And I'm using the forward here because I don't know how this function will be passed to me. Maybe it's a reference to a function object. Maybe it's a standalone function. Maybe it's a lambda. I just forward it. I don't care what it is. Just give it to the next guy. And the loop here is just applying function f to the values of my 2-dimensional arrays. This is an intermediate step that hides the ugly details, right? The call is actually like this, right? Do loop, rank, t, value, go, x, etc. It's quite ugly. If I want to write the same thing in the, if I want to write in main, I can use it directly. I can write something like this. I can do a do loop, rank of x, but rank of decal type of x, because it's not the rank of x, it's the decal type of the type of x. Then I do colon value to get the value of the rank. And then I do go and colon go. And so I go with the static member function, and I do exactly x, pass x, the data and the type. So. And how efficient is this? Well, it's as efficient as writing 2 for loops and iterating over your array. It doesn't get more efficient than that. It doesn't get less efficient than that. It just gets as efficient as iterating over an array. If you apply optimizations, this intermediate step will disappear. Also, calling the go will go away, and everything will be basically in line. Maybe go will stay, but because the compiler might say, okay, there is a loop here, you just do a function call. But that's the main idea. So, what do you think about this example? Yeah? Wait a second.
Given that we know the array bounds at compile time, would the compiler unroll it, or could we use...
Oh, yeah, this is compile time known. Yeah, the colon value there is known at compile time. Good point. Yeah, the compiler...
Unroll it?
Yeah, can do unrolling, can do everything he wants there.
Or could we force unrolling by another template recursion somehow?
In this case, you don't need forcing. You might force sometimes, but the fact is that you need if you need the bounds at compile time, there must be somewhere the constant value getting in, or you can unroll by end. But in this case, it does everything. It can actually vectorize this array if f is good enough.
We could write another template function that does recursive unrolling here, right?
In the case of multiple dimensions?
Well, for the inner one at least.
Yeah, I guess so. You could actually do looping in multidimensional looping using recursive templates. But I don't know if I understand your point here. This for loop goes from 0 to a value which is constant time. It must be constant time. It's a meta function. So the compiler here has total freedom. So I don't think you need an extra template
Well, I thought if we help him explicitly unroll it, it would probably vectorize it better.
Oh yeah, but you have to write the code for it. You can put it inside the template and specialize for it, but you have to write the hand tune the and unroll the version somewhere. The same thing here. If I want to specialize for 3-dimensional arrays or 4-dimensional arrays, in this case I have to write explicitly these specializations. And so this is a kind of a first approach to this problem. We'll need to write a lot of code for different dimensions.
So, Mauro, I have two questions. If you don't know the size of int of the array, you know it only at runtime, then when you build your API, you provide two implementation?
That's a good question. This API doesn't deal with that. And I show you in the next slide how to deal with it. I deal in this example by giving you a compiler error if you don't do it, if you pass something that doesn't have the sizes. Otherwise, you must have this runtime checking. But the API has to change. If I don't know the runtime size, I need to pass the size somewhere along the arguments here. Okay, I cannot deduce the size of the array inside the function at compile time. No one is telling me that. So I need to pass like pointer and size, C style thing. By the way, I've never seen me very seldomly using array notations in C++. You do it really for very simple code. But if you have complicated code, you just use a class that embeds the multidimensional array somehow. So this is just a kind of toy example.
And my second question, the function f is in line inside in a loop?
Yeah, typically it is. Yeah. If you optimize it, it will be in line. It depends, right? If this function f is not a lambda, in this case it's a lambda and will be inlined. You can be quite confident that things work nicely. If here you're passing a function pointer to a function which is in some other translation unit or in a library, that of course cannot be inlined, or can be in line with the link time optimizations that seldomly work very well. Other questions? I think this is the first example in which we see the old stack, designing an API, implementing it, and you can see I cannot decouple this guy. I cannot say, oh, I'm doing this because it is efficient. It is efficient to do what? It is efficient to do this. And not doing anything else, just efficient for doing that one. And as Maxime was pointing out, there might be problems here. If I pass an array which doesn't have that doesn't have runtime size, I get a compiler error. Basically because the extent in the first dimension will always be 0. Maybe it works, but it doesn't do anything. I don't remember. But you just get the wrong result. And if I pass some other thing, that doesn't really work. So suppose I want to have my object of type A, and I create this object, and I pass it as data to my looping. This will give me an error because the rank doesn't work for types, like for any type. It works just for arrays. And the template substitution will fail. And you try to go to the primary template. But as you can see, the primary template doesn't have an implementation. It's an incomplete type. And you get an error that says, sorry, incomplete type inside somewhere. So you get a long error message saying, from this line in main, and this line in the looping, and this line in this thing, oh, I got an incomplete type. So it's important to, when you get the error message, to go through the whole thing. I'll be able to show you this with this example. This is the first example. If I'm allocating my array with a new statement instead of allocating on the stack with the prefixes sizes, I I get that the dimensions are not known, and so the loop would not work. So what they do is to add protections. So you either have a strange runtime behavior or you have a strange compile time error. If you're building, this is a very simple and basic example with just one layer of abstraction between two interfaces. But when you're building more and more layers, then the error can get really, really weird because it happens somewhere. Even though it depends on your code, because you made a mistake at the user level, the error appears down there in the line. So instead, we should always try to protect the user and give meaningful error messages, either better error compiler messages or preventing the code from running in a bad way. So to add the protection, we can use static assert in this case. STL provide an isArray meta function that is true if the data type you're passing is an array, otherwise is not. And so you can say, well, if this is not an array, you just barf say it's not an array. So in the first case, in the case of passing A, this will give you an error saying, oh, listen, the type you're passing to the looping is not an array. And the second one, I want all the dimensions of my array to be specified at the compile time. So I wrote my own meta function, which I called isCompleteArray. And then I put a message there. All dimensions should be known. So if I pass an array that doesn't have all dimensions, I will get a compile time error. The code would compile and run something. It would do something probably, but with this, you get a compile time error saying you have to pass something which is known at compile time. Just to complete the example, this isCompleteArray use the same strategy of the rank, which checks if it is an array and if the array is complete. And we need this because of some technical thing. If you try to do it, you will get an error, so you add that. We check again if it is an array. But this is a good thing. We check twice, basically, but you get the error, the most specific error that is not an array early, and then you get this one. And then you implement another recursion that's basically doing a reduction with the AND operation. If T is an array of size n, then this is true. This has size specified. And you check that the next one is also the size is specified. And if you get this one, you get a false. Or if you get a T pointer, you get a false. And there you get, and there you get the end. And then you get the false because false and something is always false. But this is just an implementation of this meta function that I wrote. Let's see if we can get the code to compile. Is this one? No, this one is just rank, right? Oh no, he has everything, yeah. Okay, the code is a little more complicated than that. I'm actually using the looping. What is funny about this API is that allows you to do stuff like this is that then you can use it for everything. For instance, I'm initializing my data using my looping function. And then I'm doing my test using my looping again. So this is the code that I wanted to. This is the code that I wrote basically in the slide. This prints out the data. And this is what I wanted to develop, to show you the example. And now I realize that, well, I can, why? Then I can use these also to initialize my data. So I just use it, and it works. Oh. Okay, is this the one? Rank protected. This is the one with the static assert. So let's say that we do the looping with A. Rank protected. You get a static assert, saying the data passed to the looping must be a complete array type. T is not an array. And you have so the error message happens in a certain line of code inside the library. There should be also an instantiation line. The first one is in the instantiation looping. And requested from rank protected CPP under 43. So the error happens inside your function, inside your library, but the instantiation of the error happens here. Sorry, the problem is in this line. So if we go, so the error is in line 102. So you go and see, what is the error? Oh, the error is here. Oh, the library is wrong. So you go in line 102, and you go here and say, well, you know what? The error is up here. The actual error is issued in line 143, which is here in this statement. So there is a problem in this statement that triggers the error there. So it's not clear if the error is in the library or is in the user code, but usually if the library is protecting you with static assert, it means you're doing something wrong at the user level. And you have to read all these instantiation things. Let's try with A. This is tricky now. Okay. Is int stack I don't remember what is the what is the syntax. U35, okay. Oops. No. Oh, shoo. Okay, good. Wrong. I'm not familiar with these array notations here because they tend to be not useful at all in real life. So this is a static assert. The data passed to the looping. The data passed to the looping must be a complete array. Well, the error is wrong. It's not. That's the wrong string. It's not a complete array. So it's the line. What? Is under 43? Yes. Something wrong here. Okay, strangely enough, why is not an array? Should be an array. Anyway, the second error is actually the one that matters, but it is the first one that puzzled me. If we don't put the protections, if we don't put the static assert, you just get errors somewhere else. So if I don't put static assert, Here you get the instantiation of incomplete type of do loop, and you don't know why. Or if I do the type A, this will be the same thing, I guess. Incomplete type of this guy. So adding protections helps your user to understand what's going on. Usually if it's a static assert, it means there is something that has to be fixed in your code. I have the example with the trait classes. One notice about debugging, how to do the debugging of these things. Sometimes you get a type and you have your template metaprogram that maybe compiles, but it does the wrong thing and you don't know how to debug it. You cannot put printfs because you don't have access to the types in a nice way. So one trick is to insert into your code some type name that doesn't exist. So you are expecting the value type is an integer, right? Then you do, okay, let's check it. Type, value type, column, crep type equal to something. And that gives you an error. Say, okay, integer doesn't have crep type in it. So you know that it was an integer. There are tricks to get, you can use also static asserts to check when you're writing the code that something is wrong or in which point it is. They're all tricks that you have basically to learn on your skin. But these adding a type that doesn't exist is actually the best trick that we have found so far to check that something's happening. And ideally, it's only for library developers, so who's using the library doesn't need to do that.
So we've been talking about this for many years. Isn't someone working on debugging tools, at least for the compilation of templated code, just to get the first few error messages out of your 50 megabytes, for example? There's got to be someone who's working on tools like that.
There are tools. The problem is that sometimes those lines are useful. Sometimes that error message really need to be investigated. There are tools actually to do metaprograms in a shell-like, like in a Python-like environment. So you write your template meta programs in a kind of shell, and you can test if they are doing the right thing. There have been efforts using Clang compiler to inspect the code and be able to do some analysis, so you can actually access the types and see what they are. There's no established technique. I say debugging metaprograms still is a kind of a craft that you have to learn a little bit.
So you don't use any of these tools?
No, I don't. I have a tool that I wrote my own tools, right, to basically strip down templates. So sometimes the type here the type are very short, right? It's the type and a little bit of the string. But when a type is long, like covers half of your screen, and with small fonts, that it becomes very tricky to see what's going on. And I have tools to strip down these templates to get a shorter version of it. But still, it depends how much you want to strip. If you strip too much, you miss important information. If you strip too little, you get confused. So it's very tricky. So I do it by hand, basically. Any questions? Who finds these things interesting? Who doesn't find this thing interesting? You can say, I don't buy. Okay, so I had a very nice example with the traits, and we might go over it maybe if you have time later on. I don't want to skip the static initialization thing because I don't want to be the only guy showing you complicated stuff. But then maybe 15 minutes. How long do we need?
Generic programming, I think 20 minutes.
Generic programming can take 20 minutes or 20 hours, depending on the thing. So, yeah, let's go with the static initializations. Yeah. So we are switching the computers.